does this mic work? I think. Hey, everybody, can you guys hear me through this mic? No? Yes? Okay. Could you please, sorry for not telling you this earlier, but could you please, if possible, not bring food into the room? The trouble is, there are rats at MIT, and food crumbs attract those rats. And we want to have a smooth conference for 3 days, so maybe on the last day. No, please don't do it on any other days. Drinks are fine, coffee is fine, but please, none of the breakfast items inside. And if you do have some, I just want to request you to go outside, finish eating, and then come inside. We still have time. All right? And please let other people know if they have food, that they've brought inside. Thank you. Thank you. Awesome. This should be instantaneous. Okay, that works. I'm good.
You're good?
Awesome. Thank you.
just
Yeah, that's perfect.
put this over.
Thanks so much. I mean, it's for coming. I mean, I'm really looking forward to
Oh,
it.
I'm delighted to be
Yeah.
here. Yeah, I really am.
Like, yeah, I've been collaborating with Viral for a long time, and he's John Gilbert's student,
Yes.
and yeah, John Gilbert was also one of the other people I applied for.
It's going to take a.
Yeah.
Do you expect more people to come, or you just take them?
I think more people. Let me go outside and make sure that there aren't any.
Okay.
Is that the computer just going to sleep?
Yes, it is.
I didn't do that, did I?
No,
Okay.
we just decided.
Yep. Okay. I was trying to see if I could get these lights to go off. Do you
Well,
want to see? Do you want?
they're going to be videotaping me.
Oh, so they might.
So they
don't
want,
to
yeah,
see
see,
you.
they want to see me. And then the screen they'll capture as well. So yeah, they do want to have enough light on me.
That's a good point. I see. So they know what you're doing.
Yeah.
Okay.
And I checked
Usually
my
if I just kind of like rounds this out, because that might be the compromise that's needed to get you.
Well,
Yeah.
and I double checked my slides.
Yeah, I think back to what it was. Because I want to know if you can get this light on. Yeah. But I know you got to get Tim. Right. So you can do the. Yeah, you said two. Oh, it's just a different. So is that what it's up to those lights?
I don't believe so. I'm not intimately familiar with the way this room is set up, but it doesn't seem like it. That's right.
Yeah, let's do it.
Kill the lights.
Yeah, let's kill the lights. They might be at the back. Yep. Lights on for the video.
You need the lights on. Two is the professor. Yeah, so it has to stay there.
Should I start? Just check. Okay, perfect. We are live streaming now. Hello, everybody. Welcome to JuliaCon. We are so happy you're here for the first in-person JuliaCon in 4 years and the 10th annual JuliaCon. So before we get into things, I just wanted to go down the memory lane a little bit. Just wanted to say there are many things to celebrate this year. As I said, 10 years of JuliaCon. We started off in 2014 at Chicago at the Gleacher Center. I couldn't find a picture from there, but I'm told there are around 80 attendees, so 80 early adopters of the language. And I love this cartoon map. I don't know who made this, but this is an awesome cartoon map. Next, we moved back to our home, MIT. Well, one of the homes. Julia is international, of course, but one of the homes, MIT, and we were about 200 strong. So you can see a picture here. You can try and spot yourself if you've attended from 2015. I can spot myself somewhere around here. I looked so different. Anyway, so we moved to 2017. That's the sort of steady increase here, so around 300. 2018 at London, which I really, really enjoyed. I'd never been to Europe prior to that. That was awesome. So we grew to around 350, 360. And then at Baltimore, we grew to nearly 400. And so you sort of really saw that this is around the 1.0 time, right? And then, the language was really, really starting to grow. And this year, of course, actually before I mentioned that, we had like 3 virtual conferences in between, of course, because of the pandemic. We had over 20,000 registrations for one of the conferences. So that really sort of tells you how we've grown as a community. But then, now, we're in our first in-person conference in 4 years, and we are 560 strong. But we have more reasons to celebrate. This year's ASE 60, a conference that celebrates Professor Alan Edelman's 60th birthday. So ASE 60 is co-hosted with JuliaCon, so you'll find the ASE 60 talks on our schedule. So if you go online and click on the schedule, you'll be able to find the ASE 60 talks. They start from tomorrow. Do ask at the attendee desk how you can access them. Please check out the program, and you can find the program at the website. There are some awesome talks there. And if you are so inclined, I'm sure that they would love joining us or hosting us for those talks. What else? We celebrated 10 years of Julia last year, of course, but this is the first time we can all celebrate it together in person. And so if you haven't, please check out this really, really moving blog post on the Julia language community, on the Julia language blog, where we have testimonials from over 100 people, I think, telling people, explaining why they still use Julia today. And finally, here's a blog post you shouldn't check out. I wrote this in 2016, it's a long time ago now. 2015 was my first JuliaCon, although I didn't write a blog post about that. I don't know why. Maybe I couldn't write. There was one little nugget in there which I really enjoyed, and this is the note I sort of wanted to start the conference on. We're essentially a group of individuals, from different time zones in different parts of the world that are coming together to drive a revolution in technical and scientific computing. And I think we have a lot to be proud of just in that fact. This is a noble endeavor, and I'm glad that we're all here to pursue it together. On that note, I'd like to start JuliaCon. Actually, I do have a few announcements. Okay, so the first announcement, this is the somewhat boring part, so bear with me, but please listen carefully. Please don't bring any food in any of the classrooms. MIT has mice, and we would like to use the classrooms for 3 days. So, we don't want to ruin the conference experience with mice. So please don't bring any food in there. Coffee and drinks are fine. Make sure to check the schedules online, but do check the registration desk. There are sort of very useful leaflets over there, as well as, a bunch of volunteers who can guide you around. The conference happens at 3 different locations. So this is one of those locations. There's also the ground floor of Stata where you just came from, and the 4th floor of the Stata Center. Okay? And how do you get to the 4th floor? There are 2 flights of stairs, and there are 2 sets of elevators. And we can point you to where those stairs and elevators are. Okay. Next. Let's see. Next, we will have food trucks today. So, food trucks will have food available for purchase. They are parked right outside Stata Center. We'll point you in the direction, during lunch. Another note is, please do not go anywhere else in the Stata Center except the ground floor and the 4th floor, because this is an active workplace. We don't want to disturb poor graduate students who are trying to graduate. Okay. If you're interested in volunteering for next year's JuliaCon, please come find us, of course. There will be a poster session today, and there will be appetizers, that are served during the poster session. That'll be on the 4th floor of the Stata Center, so where the Star and Kiva rooms are. Okay. And the final thing I wanted to say before I hand it off to Viral is I have a bunch of people to thank. Firstly, I really wanted to thank all my colleagues in the organizing committee. They've done a phenomenal job just to put all of this together. I think, this is nothing sort of remarkable. I also would love to thank the AV people, lots of MIT affiliates and MIT people we need to thank, including our generous video streaming people, MIT AV, the MIT Copy Tech who printed our posters, MIT Facilities who helped us organize all of this together with all of the equipment, the tables, the easels, and whatnot. Who else? And MIT itself for letting us host the conference, right? So a lot of folks to thank. Also, actually, first and foremost, I also would love to thank the sponsors. Our platinum sponsors, Julia Hub. Our gold sponsors, ASML. Our silver sponsors, Pumas AI, QERA, and Relational AI. And Mr. Jeffrey Sanoff. Who has been contributing to JuliaCon for a number of years, since as far as I can remember, maybe 2015, 2016. This is awesome. Our bronze sponsors, Jolan.io, Beacon Biosignals, MIT CSAIL, and Boeing. Our academic partner, the Polish National Agency for Academic Exchange, and our local partner, Postmates, who, by the way, are giving out a free coupon for $25 to all of our attendees. The code is multiple dispatch. All you need to do is download the Postmates. Postmates app and order within the Boston area, and you get a free meal. All right. I think. Oh, we also want to thank our fiscal host, NumFocus. Well, what else is there to announce? There are one of the tracks changes rooms every day. I'm not going to tell you which one. It's a surprise. So what I'd recommend you guys do is keep checking that schedule for where the room is, and go to said room. You'll get used to it. Trust me. It might take you a while, but you'll get used to it. But yes, one of the tracks do change rooms every day, so make sure you're in the right room. Right. On that note, I would like to hand it off to Viral, the Julia co-creator. Would like to say a few words before we get started with our program. Thank you.
I'll echo what Ranjan said. It's so great to see everyone here, and this is the biggest crowd I've seen in forever. I found the oldest JuliaCon T-shirt I could find, and I believe it's 2017. I wonder if anyone has an older one. The only thing I wanted to sort of step up here and say is that this conference would not have been possible without the incredible hard work of the organizing committee. And I'd just like to point out all the committee members and have a round of applause for them. So Ranjan, first and foremost, as the executive chair of the conference, this all would not have come together without Ranjan. So I mean, you all know who Ranjan is. So we got Katie here, who's been tirelessly organizing the schedules. Is Katie in the room, or she might be at the registration desk? So one of our tireless volunteers. Michael Herbst, probably also at the registration desk. Michael has been the program chair. Thank you. So there we go, Michael. We got Mark Kitty-Sopikul and Avik as finance chairs. The conference is becoming more and more expensive to run. As everyone noticed, the tickets have been more expensive, but they've done a phenomenal job rounding up the sponsors and keeping costs as low as possible. So a round of applause for them. Oscar Dawson is Oscar in the room? Oscar's been a tremendous pillar for keeping the jump track going in every JuliaCon. It's kind of like a mini conference, so he has to pretty much do all of the roles for that. So, round of applause for Oscar. We got Kevin O'Brien and Stephen Kell, who've been manning all our social media properties. Every time you see a mention online, on Twitter, on LinkedIn, it's one of them. And if you see something like that, tweet, repost it, reshare it, hit all the buttons on any JuliaCon post or Julia Lang post. So round of applause for social media chairs. We've had Pablo Zubieta, who's been managing the website, and is Pablo here? Also probably, unfortunately, all the committee members are at the registration desk, but, oh yes, Pablo, thanks. And we have Ray Kimmerer, who has tirelessly wrangled with all the local arrangements at the conference, and is also continuing to wrangle things as we speak. This has been extremely smooth and way smoother than any past JuliaCon, and it's a credit to the committee. So final round of applause for Ray.
Hi. We just wanted to make one more announcement on behalf of the video streaming team. If you guys could bunch a little closer, there's plenty of open seats here. We don't need to stand on the sides and in the center here because that could block video. So if you're able to please find open seats and perhaps bunch a little bit closer because there are plenty of seats out in the center as well. Thank you. Yes. Now we shall finally get started. To introduce our first keynote speaker, Dr. Tim Davis, I'd like to introduce Professor Alan Edelman.
Welcome, everybody. Before I introduce Mr. Sparse himself, I'd like to welcome you all to MIT. I've taught in this lecture hall many, many times. This is one of the largest lecture halls on campus. And it's a funny thing, the students don't always come to class. If I were to think of this as a matrix, with my students, it's usually a sparse matrix. But I'm looking today, and I would say that this is a dense matrix. So let me welcome you all to MIT, and let me introduce Tim. So Tim Davis is Mr. Sparse, or in my mind anyway, and he's responsible for sweet sparse, and he's certainly very sweet, but his accomplishments are certainly not sparse. Tim's a professor at Texas A&M, and he's a graduate of Urbana-Champaign in Illinois in '89, which was the same year I graduated. And one of the first things that I did when I graduated was fly off to France, to a city in the southwest called Toulouse, at a center called Surfax. And one of the first folks that I met there was Tim himself. And I always have a lot of respect for people who come from non-English speaking countries and come and live here in the United States, because I went off to France, and listening to French, which I barely knew, going very, very fast, was very, very tiring. And it was really a great pleasure to listen to an American accent as often as I could. And Tim was just very, very kind to me throughout my stay over there. We had a lot of good times back then. Tim's got a lot of honors. He's a fellow of SciM, of IEEE, of ACM. And he's now at, I think I said this, but he's now at Texas A&M University, and he'll be our first plenary speaker today. So here you go, Tim.
Well, thank you, Alan, for that kind introduction. Yeah, we do go way back. It's before Julia existed. We were there. It's at Surfax. The first French phrase I learned was "Je travaille au Centre européen de recherche et de formation avancée en calcul scientifique." That was my first French phrase. You can't. It means a European Center for Research and Training in Advanced Computational Science, or something like that. So yeah, I would make all kinds of crazy faux pas. I just dived in. I'll say this joke first in French, and then the French can laugh, and then I'll translate. J'étais dans un parc et j'ai voulu dire, j'ai un cerf-volant avec du fil, mais il manque du vent. Mais j'ai dit, j'ai un cerveau long avec du fil, mais il manque du vent. So what I wanted to say, and that was totally by mistake, and 3 of you clapped. So what I wanted to say was I have a kite with 2 strings, but I need the wind, but what I actually said is I have a slow brain with 2 girls, but I need the wine. Really, totally by mistake. So that was our time in France. And in France, actually, I did the start of what is now / in Julia. This was in the Eocene era. What year was that? 1990. I started work on UMFPAC, which is the sparse LU factorization in sweet sparse, which is also part of / in Julia and MATLAB and Octave and R and Mathematica. And it all started there in Surfax. Today, though, I'm going to talk about GraphBLAS. This is a package for doing graph algorithms in the language of linear algebra. So I'm going to talk to you about that, but it's also a package that can provide fast matrix operators for Julia, for MATLAB, R, Octave, and so forth. And I'll also talk to you about some of the updates in my sweet sparse meta package, which is a collection of sparse matrix package. So this is all my work here. The Julia work, though, is by Ray, Kimmerer, Viral Shah, and others. And so, first of all, graph algorithms in the language of linear algebra. It's been observed for a long time, and what GraphBLAS is trying to do now is make this happen computationally in a software package to support a kind of, if you will, if I can say, MATLAB for graphs. In other words, a Julia for a package that allows high levels of abstraction to write graph algorithms. And to do this, we can use something called a semi-ring. And GraphBLAS does something beyond a semi-ring I'll explain. But what is a semi-ring? A semi-ring is a way of redefining matrix multiply. Matrix multiply in the conventional case is the plus times semi-ring. So to do the dot product, you pairwise multiply the terms aik times bkj using the times operator, multiply, and then you sum those up into a number. That's conventional matrix multiply. The monoid here is called the plus. That's the summation. And that monoid has an identity value of 0, which is to say x plus 0 is equal to x. Now, in the sparse case, things change just a little bit. We don't need to do the summation over the entire vector. Instead, we just apply the multiplicative operator, the times operator, on the entries that appear in those two vectors. In other words, we're computing a set intersection in the dot product. And so if Aij, if calligraphic Aij here is the non-zero pattern, but that's going to change, of the ith row, and if Bj is the non-zero pattern of the jth column of B, then this is done across the intersection here. So that's the conventional plus times semi-ring. Although I need to add that this is actually not always the fastest way to do sparse matrix multiply, but this is the way to think about it. Now, this is not the only way to define matrix multiplication. For example, there's a thing called the min-plus semi-ring called tropical algebra, because it was invented, I think, in Brazil. And here, the monoid is the min operator. And instead of, and the multiplicative operator is plus. So in that dot product, instead of multiplying pairs of numbers together in the intersection, we sum them. And then reducing those numbers down to a scalar is done using the min operator. And so the definition of matrix multiply for the term Cij looks like this. And now the identity value of the monoid is plus infinity. The thing not there is now plus infinity. And in the sparse matrix, the chairs here that are empty would be filled with the number plus infinity, conceptually. Although in GraphBLAS, that value is just not there, because a matrix can move from semi-ring to semi-ring. So that's actually breaking the notion of a semi-ring a little bit, or extending it. But the value not there depends upon the semi-ring it's used in. And so we don't actually need, though, because when we're computing over the set intersection, we're computing on the structure of these matrices, we don't actually need the monoid value computationally. It's just a convenience mathematically. Sometimes I use it, but we just have to reduce these values across the intersection. And if there's no intersection, then Cij is not the identity value, it's just not there in the matrix. It's an empty chair. So a true semi-ring has lots of properties. It has the plus operator, which is a monoid, which is an associative operator with an identity value. It's also commutative and associative both. And so it has all these nice properties. And we keep all of this in GraphBLAS. The star, the multiplicative operator, is an associative operator with an identity value of 1. It has all these nice properties, and it distributes as well in particular. And this means that the matrix multiply of A times B times C can be done in different orders. Well, we break that. So GraphBLAS does have true semi-rings, but we also have different kinds of semi-rings, or an extension. And I'll show you why we do this, because it's useful for creating graph algorithms. But I needed to first introduce the idea of the semi-ring to redefine matrix multiply. And what we do in GraphBLAS is we X this bottom part out, and the multiplicative operator is just any binary operator. So it's a pseudo semi-ring, or a semi-pseudo ring, or pick your name. I'll call it the GraphBLAS semi-ring, or just a semi-ring, and just bear with me mathematically. And also, the domain, there can now be 3 different domains. The domain for the matrix A can be different than the domain for the matrix B. In other words, the value, the data type, can be different from C itself. And that's very useful in many graph algorithms. And speaking of that, GraphBLAS allows for arbitrary data types. It has different sizes of integers, different sizes of floating point operations. And if you want new ones, you just make them up, give them to me, and I'll just do it. So one of the collaborations I'm working with is a company called Permian.ai, and they need a Gaussian integer, which is an integer with complex and real and complex parts. You just define it, you give it in. You don't have to recompile my package. It just does it. I'll explain how I do that later. So why are summarings useful? Why are sparse matrices useful for graph algorithms? Well, I mean, if you're inside Julia, you don't write a triply nested loop. If you're inside MATLAB, you don't write a triply nested loop to do matrix multiply, right? You want to live in a higher level of abstraction. You just want to do A star B and then let somebody else handle that. The same can be true for graph algorithms. Graph algorithms often have this pattern, this double or triply nested loop. For every node, do this. For every edge, do this. And if something is true, do this. That pattern of computation, if you sort of take your glasses off and squint, looks just like a matrix multiply, but, well, just pull out that operator and put a different one in, and then you get a summary. So here's an example of, one example is the all-pair shortest path. If you have a weight matrix, where Aij is the weight of the edge ij, and you use the min plus summary, and you raise the W matrix to the n minus first power, then you get the all-pair shortest path. Problem solved. If you use the tropical min plus summary. And here, the thing not there is is plus infinity. So if you have this empty chair, if you will, that corresponds to an edge that does not exist in the graph. Now that's an edge not existing in a graph is very different than the existence of an edge of any weight at all, right? An edge even that's plus infinity, that's an edge. Or an edge of weight 0, that's an edge. Not an edge is different. So in the sparse case, in GraphBLAS, we look at the matrix as really two things at the same time. We consider both its structure and the values of the entries in that structure. And those are both important in a graph algorithm and in the matrix data structures as well. So here's an example of the use of a logical or Boolean summaring. Here in the Boolean summaring, we don't use plus times, it's or and. So do a logical and then the monoid, summing them up, is the logical or, which of course has nice short circuit properties, which I exploit. You can stop early if you come across short circuit or, for example. So here is a working pseudocode in sort of pseudo MATLAB, which of the breadth first search. And here the matrix is Aij is the edge from I to j. And here is the source node, and suppose we're at frontier 1 and 3. And what this algorithm is doing is computing every level in one outer loop for each level. So here we're at level 2, next level. We want to discover the next level. And so the first thing that happens is the Q is a sparse vector, and it represents, in this case, a sparse row, and it represents the non-zero pattern, not represents the nodes in the current frontier. In this case, it'd be entries 1 and 3 would be present in the vector Q when I'm at level Q wanting to compute level 2 wanting to compute level 3. But if I want to save the level of these nodes, I can do that with this assignment statement here, which is a masked assignment, or in MATLAB or Julia, it's logical indexing, or V of Q, where Q is non-zero, assign the current level to that position in V, which is going to give the level of every node. And now if there's no end nodes, break, and then finally the Boolean summaring. So what happens here is, if you think of the flow of the matrix vector multiply, which I think I also have on the next slide here with this picture, but let me stay here for the moment. So what's happening here is, if you think of the nodes 1 and 3 in the current frontier, we want to compute the next frontier, level 2. So we're going to take nodes 1 and 3 and form the set union, not the set intersection, of their outgoing adjacency lists, which is 2, 4, and 6. Oh, 4? I know what 4. I've seen 4 before. So drop it out. And in breadth first search, there'd be an if statement at the very center of that innermost loop. What we can do in a matrix notation is hoist that up to a level called a mask. At a matrix level, using the mask, and that's shown right here, where a node that does not have a level gets the assignment. So the mask works as follows. Imagine you have a matrix, and you do an assignment into it. It's a bulk if statement. You put your hand over the matrix, that's the mask, and you can write to this position but not to this one. In other words, you can write or not to this one, sorry, because the mask is in the way. So the mask tells you where you can write to the output or not. And that's a matrix level way of expressing the if test inside the innermost loop. So in other words, node 4 already has a level, so it does not get included in the output. The output of this matrix vector multiply here will just be nodes 2 and 6. So here's on the left, and we can do more with different summaring. So that's the Boolean summaring, but there's more with a really strange summaring called the any second I, I'll explain. So the traditional breadth first search is on the left in pseudocode, and it's got that doubly nested loop for every node in the frontier, for every edge. If it's not seen, add it to the queue, and so forth and so forth. You've seen this, and you see there's an if there. This traditional breadth first search has several problems with it. It's simple, but it's not parallel. If you have to write it in parallel, it's very hard to write. You need access to, or you need to write your own graph data structure, or have access to one that's going to help you. And if you have a library that helps you with the data structure, but if you want to write this kind of algorithm, that library is going to be serving you up one edge at a time. Oh, you want here's the next edge, here's the next edge. It's really hard to make that fast. It's possible, but it's a very fine-grained level of description of this algorithm. It's rather like writing A star B in MATLAB with triply nested loops. You wouldn't do that.
Because nobody here uses MATLAB, right?
No, you wouldn't do that.
Because everybody here uses Julia.
So it's akin to A star B
In Julia.
Okay, you wouldn't do that in any language, the high-level language. So what about the GraphBLAS breadth first search? I'm going to use a rather funky pseudo summaring. And the mathematicians will cringe when I describe the monoid, I hope. And so here's what this looks like. It looks just like the last one, but I want to do more. I want to compute the breadth first search tree. In other words, I want there to be a tree where 4 is the root. Its children are 1 and 3. And the children of 1 is 2. And so child of 1 is 2. And the children or child of 3 is either 2 or 6. But 2 has 2 parents. That would not make it a tree. I have to pick one of them. Node 2 has 2 candidate parents. And in the tree, just pick one. Any one. All right, so now think of the dot product. Okay, and I also need to compute who found it as well. So I'm going to let the summaring do both of those things in a single matrix vector multiply. We're going to ask who found you, and then if multiple nodes can be your parent, I'm going to pick one, and do all of that in A star Q. So what does that? Well, first of all, the multiplicative operator. Imagine the dot product. What I want to do in that dot product is I want to know, I'm multiplying these matrix times vector, but I don't want to know the value. The matrix is just structural anyway. There might have weights in it, but I just want to ignore those weights. I just want to work on the structure. Does this edge exist or not? And the outcome of this, the output of this dot product needs to be the value 1 or 3 for node 2 here. The dot product here would say, oh, 1 and 3. Oh, look, I could be either coming from 1 or 3. And so I want AIK times QKJ. If I go back here, I want the value of this expression here to be the value k itself. In other words, I want to redefine aik times bkj to be equal to k, which is not the value from the matrix or the vector. It's the position of those entries in that matrix or vector. So that's what I call the second I operator. I call it second I because it's the row index of the second operand. So you could imagine first I would be I itself for this expression. And second J would be 1, or 0 if you're zero-based indexing. It'd be the column index of the second operand would be the second J operator. Well, so I'll make it second I. And so now for node 2, I'll get the numbers 1 and 3. Now I want to collapse these numbers 1 and 3 to a single number, and that will be the parent of node 2. Well, I can't use a plus monoid. I would get 4, and 4 is my grandparent. That doesn't make any sense to add node IDs. I could use the min monoid and get the number 1 reliably. I could use the max monoid and get 3. Or meh, Tim, just go pick yourself and just give me one of them. So this is an operator of choice, of my choice. And it's not random. It's not a random operator. And I call it the any operator. It's any of x and y is x or y. I pick, and if you don't like it, don't use the operator. Okay? And this is really handy. It has a rather strange monoid characteristics. I argue that it is associative and commutative, the any operator. It's pick one, any one. You have the same choice, right? If I say pick, here's A, B, and C. If I say pick one here, and then of that pick the result, well, you'll get one of 3. So if you do that in any order, you're just telling me pick one of the 3. So it's associative and commutative. The monoid value, the identity value is rather peculiar. It's really any value, because it's my choice. X plus anything is not anything, it's X. So any value is the identity value. That's what's weird about it. But then I don't actually need the monoid to compute with anyway, because I only compute on the set intersection. Why do I introduce such a bizarre, why don't I just, Tim, use the min, and you get a definitive answer. Well, it's faster, because this is a parallel package. And I've got multiple threads computing this. And I can have one thread comes up with 1, one thread comes up with 3, and then they just do an atomic write. And it's either a 1 or it's a 3. And whoever got there first loses. The one last, that's the answer. You run it again, you let the race condition, it's a benign race condition that improves then performance. You don't like it, use min. Okay. But if you like performance, use the any operator. And now there's a strange summary for you, isn't it? It's sort of like the n of NP completeness, right? I get to pick, you don't. Ha ha. I'm the oracle who picks. The other advantage of this is the graph data structure is opaque. You can just tell me, do the matrix multiply, and this matrix is a complex beast. I have multiple ways. I have 16 ways of storing your matrix for you, and I pick, depending on the characteristics of the matrix, for each data type. In fact, it's not just 16 because there's different sizes of integers and complex and double and real. No, it's 16 different data formats for each of those. Then finally, there's 2 masked assignments here. There's the first one I explained. If you don't have a parent, then you can go into the subsequent frontier. But I also need to keep track of the parent of all these nodes, which is this masked assignment as well. So there's this masked assignment happens all over the place in GraphBLAS, and so I spent a lot of time getting that to work efficiently. And it's rather like logical indexing, and it takes out that if in the innermost loop. So this is the BFS tree in GraphBLAS. Pseudocode, it's 2 lines of GraphBLAS. And it works pretty well, and you don't have to write your own graph data structure. You let me handle all the heavy lifting. And it's parallel without even looking at it, because the library is parallel. You're giving me a bulky thing to do, a matrix vector multiply. I've got a multiple core machine. I'll eventually be using GPUs, and then I can do these things in parallel. Here's another example. This is now using pure MATLAB syntax, because that's what I do. I do MATLAB, sorry. Here on the left is my implementation of a sparse deep neural network in pure MATLAB. And it's using the conventional matrix multiply y times the weight, so it's propagating through these layers. And then it has to do this funky thing to do the biasing. You have to take a column of the matrix, any non-zero in the column, say we want to add 32, I think is the number I'm doing here. The bias, sorry. Add some bias value, bias of k, to the kth column. So I'm adding a value to every entry that's already non-zero. So you don't want to add a value to the thing that's not there, the 0. So that's not a matrix add. What is it? It's actually a diagonal matrix multiply. It's scaling by a diagonal matrix. You're just in the wrong semi-ring if you use the conventional one. So the scaling effect, the adding the bias, is here. It's the plus semi-ring. So take your weight, take your y value, and take your bias as a diagonal matrix, multiply on the right. You're multiplying by the bias, if you will, every column. But the multiplicative operator is plus, because you actually want to add the number there. And so it's a plus semi-ring. This here is the conventional plus times semi-ring. And then the rest of it here is thresholding. If anything is negative, set it to 0. And if anything is bigger than 32, set it to 32. I can do this syntax as well. I have fully overloaded operations here. I could run this using GraphBLAS matrices as well, or I can make it a little bit faster using the functional form. And so complexity-wise, they're roughly the same in terms of conceptual difficulty of writing these two pieces of code. But one is 40 times faster than the other. And I'll let you can see on the screen which is which. So the built-in sparse matrix operations are not as fast in MATLAB, although, and I'll explain more about that later. And here, using GraphBLAS with a 20-core machine, 20 threads, I've got a 40x speed up. So it's not just parallelism that I'm getting speed up over MATLAB. It's more than that. What can GraphBLAS do? What tools are in the toolkit to give you these operations? Well, if you think of Julia's syntax, the star, the tick, the equal, the paren, the colon, the comma, the whatever, okay? All the non-alphabetic characters, the left and right square brackets and such. All of that GraphBLAS can do, sparse, with any data type you like, even ones you make up. Even semi-rings you make up. And then each of these can be masked. The M thing here is the masked operator. So here's a masked matrix multiply. And each of these operations also has an accumulator. So this is like C plus equals A times B, where the plus is this accumulator operator. What else? Entries have any data type. We can use any operator. So for